So with this, we'll move on to the next talk. And let me just do the introductions, Hari, first, please. Yeah, so I'll share my screen and I think you can see it. The next talk is going to be boosting performance of HPC applications with MVAPICH2 software. And the speaker is my colleague, Dr. Subramoni. He's a research scientist in the Department of Computer Science and Engineering at OSU. So he's been working as research scientist since September 2015, but he's been involved in the MVAPICH2 project for, I think, 14 years now. His research interest includes high performance interconnects, parallel computer architecture, network-based computing, and it's a long list, obviously. He's published over 70 papers in international journals and conferences, and he's very actively involved and leading the software development efforts for MVAPICH2, MVAPICH2X, and MVAPICH2 GDR software. So over to you, Hari.
Thanks, thanks, Amir. Appreciate it. Hey guys, I'm Hari. So sorry that we can't meet in person this time around. So if you have any questions, please feel free to interrupt me and ask. So this tutorial is going to be on boosting the performance of HPC applications with MVAPICH2. I hope all of you can see my slides and the pointer.
Yes,
so, since we are at MUG, probably you guys don't need the slide, but as people say, out of pure self-interest, we'll put this anyway. So as many of you know, we've been around for quite a while, and we are being used by a lot of organizations around the world. A lot of details of what we do, all of the packages that we have is available for download from our website. So in this talk, I'll be highlighting some of the capabilities from the user perspective. So this is going to be completely from a user's perspective. What are the typical gotchas? What is needed when you start an application? What are the kind of issues one might face? Those kind of things, okay? We will touch a little bit upon the design, but mostly it is going to be user-driven, okay? And I'll be discussing mostly about the open source MVAPICH2, the MVAPICH2X, and the MVAPICH2 GDR versions. How do we make sure that the code is robust? What all features do we have? How do we deploy these solutions? What are the different methods we use to deploy them? How do you utilize, enable/disable the different features provided by the different libraries, and what is the potential performance impact that it can have at the micro benchmark and the application level? So this is how the overall talk is going to be structured. So this is the overall architecture of the MVAPICH2 software family. So as you can see, we have advanced support for a lot of different high-level programming models, as well as underlying APIs and mechanisms. So all the way from like point-to-point operations to collectives to job startup, energy awareness, and introspection analysis. And all of these advanced features that we introduce is based on underlying support that is being provided by different vendors out there. So let's say if a vendor comes up with support for a new internode transport protocol, or like a collective offload protocol, or like an intranode transport mechanism, we try to see how we can take advantage of all of these features. For instance, like XPMEM or NVLink, the DC transport that Deva was talking about earlier in the morning, or user mode memory registration support for performing advanced data type transfers, using multiple network adapters to parallelize and speed up transfers. So we try to take advantage of all of the features that the underlying network as well as intranode hardware provides to enable high performance and scalable communication mechanisms for different parallel programming models. So what we do, so we are primarily a research group. So this is probably one fundamental thing that differentiates us from every single MPA library out there. So our primary goal is research. But even though our primary goal is research, we don't stinge on quality. We have a very rigorous Q&A procedure before making a release, and each commit is taken through about 18,000 to 21,000 hours of core hours of testing on our very large internal testing system. We have an automated testing procedure which tests out a bunch of benchmarks out there using OSU microbenchmarks, Intel microbenchmarks, the MPICH test suite, Intel test suite, NAS parallel benchmarks, Scalapack, Spec, and a bunch of ECP applications, mini apps like Mini AMR, Mini Ghost, Mini MD, for a lot of different combinations of environment variables that triggers a different design feature inside MVAPICH2. So that is as far as functionality goes. So once we know that the code is rock solid and everything is working fine, now we need to look at performance. Has there been any regression in performance because of any new features or any other things? This is an extremely complicated system. A small change at like a 5-line change that you make in some place could lead to like 10 to 15% degradation in point-to-point operations, which could lead to 20 to 30% degradation to collectives, and just kinds of builds up. So in order to make sure that performance degradation does not occur, we have very good and automated scripts for performance regression, which takes a couple of commits and ensures that commit upon commit, we are only improving, we are not degrading. So we have an automated procedure for that. So once we have made sure that we have the code ready, the functionality is good, and the performance is good, the next headache or the next challenge is to figure out how we deploy these solutions. So we have different deployment strategies. So we can deploy our solutions as RPMs or Debian packages, or we have capability to deploy directly on cloud platforms like Microsoft Azure or AWS directly from the MVAPICH site. And if you go to the site, we have a very detailed download page showing what all RPMs are available or Debian packages are available for which systems, for different kind of CPU architectures, different CUDA versions, different OFID versions, so on and so forth. So this is if you want to get it as RPMs. But we have heard a lot about SPAC, how SPAC is being integrated into cloud providers as well as HPC ecosystem. So I just want to touch up a little bit on how we create the SPAC deployments as well. So in order to create like a SPAC image, so we initially create a new package, edit the py file. I think all of you who use SPAC are familiar with the various recipes or Python package files that are available in SPAC. So once we make a new release, we update the SPAC package to say that, hey, this is the new release. These are the new different features. Then we test it locally, initialize the GPG keys, and then we have a local mirror. So this is the most important part where we create the SPAC binaries and upload it to the local mirror. So once it has been uploaded to the local mirror, then we verify it locally to make sure that people are able to pull it. There are no dependency issues, and trust me, there are a lot of issues that come up with binary deployments in SPAC. I believe Todd will be talking more about that in his talk later on in the conference. So once we have done all of this internal Q&A, then we raise a pull request for the new py file. Then it goes through a series of code reviews by the SPAC folks. And once it has been upstreamed, we make sure that the code works and finally make the release announcement. So once this announcement has been made, then you could clone the SPAC Git, source it as is mentioned in the SPAC user guide. Then if you want to install a particular version of MVAPICH2 for a particular compiler version, you can quite easily do that from source. Or if you want to install one of our binary versions, which is like MVAPICH2X or MVAPICH2 GDR, you could first add our mirror to your list of accepted mirrors. Then make sure that you trust the public key, which we generated in this previous step, and it is available from our website. Once you have done that, then you could find out the list of packages available and then go ahead and install the packages, either the MVAPICH2X or the MVAPICH2 GDR packages for any different version of OFED with all the different features that was mentioned in our download page on your system. Okay. So this is a brief overview of how we do R&D convert that R&D into functional working code with performance, and deploy it on different HPC systems through multiple methods, either open source or through RPMs and Debian packages or through SPAC. So what is it that we are looking at going forward? So we obviously want scalability to millions or billions of processes going towards exascale. We want to have scalable collective communication, which is probably offloaded, looking at topology awareness, the ability to have non-blocking support. So the other thing is to make sure that we are able to balance intranode and internode communication. So now if you look at some of the newer supercomputing systems like Selene, which is like a DGX2 superpod, you literally have islands of very dense compute capability, which is connected by either a few or let's say some internode interconnections. So you have a lot of islands of computation that are coming up. So how do you ensure that you're able to balance internode and intranode communication so that your overall application performance does not get affected? So with these kind of dense systems, we also need integrated support for different kind of GPUs like NVIDIA GPUs, AMD GPUs, and maybe Intel GPUs once they are available in the future. We also want to see if we can have quality of service support. So as you saw with the Rockport Networks tutorial, they have a very nice support for quality of service. So we are trying to see if we can have additional support for quality of service with tight integration using advanced networks like Rockport and InfiniBand, and finally virtualization and energy awareness. So this is let's say our plan going forward. Now let me go into some of our particular use cases, particular libraries, and discuss some of their features here. So I'll talk about MVAPICH2, MVAPICH2X, and MVAPICH2 GDR in this talk. And some of the other aspects of it will be covered by various other talks in MUG. So for instance, Jitin will be talking about MVAPICH2 on Azure. Matt Cope will be talking about MVAPICH2 on AWS. Like there'll be a talk by OSC folks on OSU INAM. So I'll not be touching upon all of those things in this particular talk. And Amir, Arpan, and others will be presenting about the deep learning support for deep learning applications in MVAPICH2 GDR, which is coming up right after this one. So what are the new features in MVAPICH2 236, which we released some time ago? So we have support for collective offload using Mellanox's Sharp v2. And we have added support for reduce, broadcast, all reduce, and barrier using Sharp here. We have enhanced performance for the UD hybrid code. We have added support for multi-rail collectives, multi-rails, and enhanced performance for shared memory collectives. We were also able to significantly improve the job startup performance for the new generation of Flux job launchers or job schedulers coming out of Lawrence Livermore National Labs. And then we have a bunch of other features, including support for the Oracle's HPC shapes, as well as a few others. So with any MPA library, the first thing that you would face would be to start up the job, okay? You could have a Lamborghini or a Ferrari or a Tesla, but if the car takes 15 minutes to start, nobody is going to buy it. So just like that, in an MPA library, especially once you're going to scale, job startup is very, very important. Now, job startup has two dimensions: the amount of memory required to store endpoint information and the time it takes to start up the job, let's say from 0 to after MPA init in how many seconds. That is basically what we are looking at. Okay, so as people say, 0 to 60 in 3 seconds. So if you look at MVAPICH2, it's more or less able to achieve that at like full system scale on the Frontera supercomputing system. So here I'm showing the job startup performance on the TAC Frontera systems at about 250,000 processes. So MPA init takes about 31 seconds for 250,000 processes. That is half system size on the TAC Frontera system, which is physics processes per node. So this is pretty damn cool, if you ask me. So if you have a very, very large job, you can start in under a minute on the TAC Frontera system. So compared to the competition, this is pretty cool. That's what I would say. And this entire talk is going to be as follows. So once we present a feature, we say what environment variables you can enable to achieve this kind of performance. So there are a few things that you can set here, and MVAPICH2 will complain fairly loudly if you haven't set this, and let's say there's a potential to do that. So with the last release, we added some let's say performance impact warnings to MVAPICH2 so that people realize something is happening and take proactive measures. So this is one thing that we have sadly figured out. Nobody ever reads the user guide. So no matter what details you have in your user guide, nobody really cares about it. They just take it up, run it. If it runs fine, fantastic. If it does not, then people don't tick. So we have added a lot of performance warnings. Sorry for our more advanced users. Like there are ways in which you can suppress those warnings, but this is meant for the more newer users who don't go through our fairly extensive user guide to figure out how exactly to get the best possible performance from the MPI stack. So for instance, these two environment variables can be set to get these kind of job startup performance at small to very large scales for job startup on HPC systems. And these are some of the other environment variables you can tweak to see if you're able to get that performance even better. Okay. So once I have started up the job, what mostly that we would need is to have good support for point-to-point communication. We need to have good process-to-core mapping strategies on modern NUMA machines and good collectives. So let's look at these one by one. So MVAPICH2 has support for different kind of transport protocols that InfiniBand has, including UD, RC, and XRC. XRC is now more or less deprecated. So let's just call it UD and RC. And MVAPICH2X has support for the dynamic connected transport protocol as well, which we'll talk about there. And this is configured at runtime by using this flag, which is again now enabled by default. And these are some of the environment variables you can use to enable or disable the support. So why do you want a hybrid protocol? So if you look at UD, you get very good scalability. But if you look at RC, you have a lot of rich features, including support for very good performance for large message transfers. So what we want is the best of both worlds, where we have the scalability of UD with the high performance large message transfer capabilities and atomic capabilities of RC. So that is what we provide using the hybrid transport protocol selection method inside MVAPICH2. And using this, we get fairly good improvements in overall application performance. And this is especially true if your application uses dense collective operations like all-to-all. Okay. So once we have tackled the challenge for a small message communication, or let's say point-to-point communication, the next most important issue that most application developers face is process mapping. This is especially true if you are using an MPI plus OpenMP or MPI plus threads application. So one of the most common issues people see is this. Hey, I have an MPI plus OpenMP application with one MPI process and 4 or 8 OpenMP threads. Instead of improving my performance 4-fold or 8-fold, it reduced or degraded the performance by a factor of 7. What the heck is going on? So what's going on is the process mapping issue. So if you are using so for performance, we always make sure that a process is bound to a core. We don't allow the process to run around. If a process runs around on a modern NUMA node, you will get all sorts of weird performance because of your NUMA effects. So we bind a process to a core. But the problem is that your threads associated with that process inherit the mapping. So if you have 4 or 8 OpenMPA threads, instead of those threads picking a free core, it will pick the same used core. Okay. So that is why we introduced this new hybrid binding protocol. So with the default bunch protocol, what would happen is that a process would get bound to a core. So instead of binding a process to a core, you can say that I want the process to be bind to a socket, so that we allow the process to run between different cores on the socket. But even this may not lead to the best kind of performance. So that is where we have these hybrid binding policies. where we allow users the flexibility to select the number of processes, threads per process. And if they are using OpenMP, then the value of this environment variable is automatically inherited from the OMP num threads environment variable, which is already used for OpenMP. And we have a lot of different binding policies here. So we have support for bunch, scatter, linear, compact, spread, and NUMA. So I'll go through some sample examples of how we perform this. So suppose you want to have a hybrid binding policy with 4 threads per process with the compact mapping. So what would happen is that rank 0 would get these many cores, rank 1 would get these many, rank 2 would get these many, and rank 3 would get these many. So this is how the process binding would work. And it would be a little different in case of like a linear binding policy. And for a NUMA binding policy, it would be like even more different. And if you want to figure out how exactly this binding policy works, then this environment variable is something that is going to be very, very useful for you. So there is an environment variable called MV2 show CPU binding, which is going to tell you which CPU set each process is getting bound to. This is a very useful environment variable which you can use, and more details are available from this user guide link. So please try this out, and please keep this in mind when you run your applications to see what process to core mapping is being used. Just like this one, we have a corresponding environment variable to show the network adapter each process is using, that is called MV2 show HCA binding, HCA as in host channel adapter. So that's also something that is very, very useful. So these would be some useful debugging tools to have in your toolkit the next time you are running into any performance issues with MVAPICH2. So we went through point-to-point and process mapping. The next one is obviously collectives. So MVAPICH2 has different support for blocking as well as non-blocking algorithms. We have what is called as the conventional or flat algorithms. And we also have multi and many core aware designs. So the multi and many core aware designs are typically hierarchical with a separate intranode and internode phase. And each phase can utilize one of many underlying transport mechanisms. So for instance, your internode communication can either rely on basic point-to-point operations, or let's say direct RDMA operations, or one of the newer network offload mechanisms like SHARP, or the older one like the hardware multicast. Similarly, for intranode, we can have different choices in transport protocols using Linux's cross-memory attach or CMA, direct shared memory-based mechanisms, and other kernel-assisted schemes. And these are the environment variables that you can use to toggle these features. And by default, all of these are enabled if the system does support it. So what's the big deal? What happens if I'm able to use support for hardware multicast on TAG Frontera? So here we show the performance of MPI broadcast or MPI bcast with and without support for hardware multicast on the TAG Frontera system. So as you can see, one can get significant benefits in overall execution time for the broadcast collective with multicast as opposed to without multicast. And we can see that the multicast-based designs improve the latency by up to a factor of 2 at 2000 nodes. So if you are running very large, let's say, broadcast operations, then this is something that you should definitely look at. And MVAPICH2 also has support to use multicast for implementing the scatter collective, and this is how you enable it. We also have support for Scalable Hierarchical Aggregation Protocol, or SHARP, which was discussed in the NVIDIA tutorial by Manju and Deva. So I will not go into too many details of what SHARP is, since they have already talked about it. But I'll talk about what benefits you can potentially get. So we evaluated the performance of SHARP with all reduce, and barrier on the TAG Frontera systems up to like almost full system scale, like 7,000 nodes. So as you can see, for all the three collectives, using the Sharp-based solution significantly improves the overall runtime of the collective operation by a factor of up to like 5, 9, or 6 for already used barrier and reduce respectively. And this is the environment variable you need to provide to enable it. Okay. So the benefits are not limited to your micro benchmarks. One can also get benefits at the application level. So this is the benefit of using Sharp for the HPCG application. And more details of Sharp and the scalable or the streaming aggregation support in Sharp will be presented by Bharat in his talk on Tuesday from 4:30 to 5:30. And for more details on how to run Sharp, please look at this particular section of the user guide. Okay. Any questions so far, guys? Again, remember, this is not an in-person meeting. I can't see your faces to see if you're doing or if you're sleepy or if you're bored. So if you have any questions, like either raise your hand virtually or put a question in QA or on Slack, and I can try to respond to that. Okay. So assuming that all of you guys are still with me, let me go on to the next section, which is talking about MVAPICH2X. So MVAPICH2X has support for a lot of newer capabilities, as well as it supports stuff like the PGAS models like UPC, UPC++, OpenSHMEM. It has support for optimized asynchronous progress, XPMM-based point-to-point collective, support for the dynamic connected transfer protocol, user mode memory registration, on-demand paying. So all of the newer features that IB offers is supported under MVAPICH2X. So I'll talk about a few of those features and the performance that you can get by using those features in the coming few slides. Okay. So the first one is looking at the impact of the dynamic connected transfer protocol on Neuron. So I mentioned earlier that we have UD and RC for the point-to-point selection, right? So UD gives you good scalability. RC is good for performance, but not so much for scalability. But do you have a middle ground where we can get the best of both worlds? So that is where DC comes in. It gives you the full feature set of RC, but with the scalability of UD. So when we use protocols like this as for very dense collective operations like all-to-all or other very communication intensive point-to-point operations, we see significant benefits in overall execution time of the application. So this is an example of the Neuron application taken on the EPFL cluster in Switzerland. So as we can see, when the number of processes increases, we see increasing benefits. And once you go to a very large scale, the default RC transport protocol has a significant overhead for connection establishment as well as communication, which leads to like a reverse trend in scaling, whereas DC is able to hold the good scaling trend as the number of processes increases. So more details of this is available in last year's MUG talk. So if anybody wants to take a look at it, and these are the different environment variables that we used to reproduce this in case you want to try this out yourself with the Neuron application. So we have provided all the details of the application that we used, how we ran it, and the environment variables and the version of MVAPICH2X we use. So if you want to try it out, please feel free to take these and try it out on your own system. You also have support for CMA-based collectives for large messages. So as your HPC systems are getting denser and denser in terms of number of CPUs available per node as well as the number of GPUs available per node, we want to have very good mechanisms for intra-node communications for point-to-point as well as collective operations. So that is where we try to come up with optimized mechanisms to use kernel-based transfer mechanisms such as CMA for large message transfer. So Here, we look at the benefits that you can get if you use CMA-based collectives for large message transfers for different like collective algorithms. So in this particular slide, we are looking at the gather collective on the older generation Knights Landing platform with 64 processes per node. But again, the trends hold on other more traditional platforms like the Intel x86 Broadwell and the IBM OpenPower architecture as well. And this also gives you good performance for other collectives like Broadcast, AllGather, and All2All. So Manju in his talk talked about how do you have good asynchronous progress. So one way is to offload to like a intelligent network. But what if you don't have an intelligent network to offload your collectives to? What do you do then? Is there a generic way for us to have offloaded collectives or asynchronous progress capabilities? So that is where we try to add support for a new, more optimized asynchronous progress design in MVAPICH2. So this has a CPU-based progress thread per application process. But instead of being always active, this is only active when asynchronous progress is actually required. So instead of always taking 50% of the CPU away from the application, it only becomes active when communication progress is required, then goes back to sleep. So with this, we are able to get good overlap of computation over communication without sacrificing additional cores. So this is something that is pretty cool, and something which we feel will give a lot of benefits to end applications. So next we go on to the shared address space or XPMM based designs. So here we have performance benchmarks with different kind of collective operations like reduce and all reduce. So we see that the XPMM based solution is able to significantly improve your performance in the medium to large message range by several factors for both reduction as well as non-reduction collective. So we had introduced the support like about 2 years ago in MVAPICH2X, and we were the first people to do that. Since then, a lot of other MPI libraries like MPICH as well as OpenMPI or HPCX have added support for XPMM-based operations. So the benefits are not just limited at the microbenchmark level; they are quite easily transferable to the application level. So here we look at the performance of CNDK-based AlexNet training as well as mini AMR. So we can see that by using XPMM-based designs, we are not only able to improve the performance of reduction and non-reduction based collectives at the microbenchmark level, we are also able to significantly improve the performance of the applications as well. So I think Benson has a question here. So it is, have you looked at the interoperation with different SYCL implementations? No, we have not started looking at SYCL yet. So far, we have added support for the AMD GPUs as well as the NVIDIA GPUs. We still don't have access to the Intel GPUs or the entire one API SYCL environment. We are compatible with the Intel's IFX compilers, which has support for one API. But since we don't have any dedicated funding along that direction, we haven't had a chance to explore further. But it is on our roadmap for the future. I hope that answers your question, Benson. So with this, I come to the end of the MVAPICH2X section. Before I go into MVAPICH2 GDR, does anybody have any additional questions or comments? Okay. If not, let me proceed into the MVAPICH2 X or MVAPICH2 GDR section. So what is MVAPICH2 GDR and what is the big deal about it? So typically, if you look at GPU-based applications, what is the modus operandi? I take the data from the CPU to the GPU do my computation on the GPU, move the data back up to the CPU, transfer the data from one node to another. So this was the modus operandi a long time ago when GPUs first came into the HPC ecosystem. But then we asked a question, is this the best possible use of the application developer's time? Like writing code to move data from A to B, B to A, isn't data movement that the responsibility of the MPI library? Shouldn't the application developer just launch the kernel and then tell the MPI library that, hey, move this data from GPU to GPU? So that core idea, that simple idea is what we try to use in our GPU work. So this is typically how the modus operandi is before. So you could do a CUDA MVAPI, you do a send, and then you do a CUDA MVAPI. Okay. So this is high productivity probably because it's very easy to do, but very low performance. Okay. Now the application developer can write an extremely complicated piece of code to do a pipeline transfer and then try to overlap the internode transfer with the intranode transfer and get pretty good performance. But the problem is there's a heck of a lot of code that you need to write, and there are about 14 different paths for you to go from here to here, depending on the relative locations of the GPUs and the network adapters. So this, while gives you very high performance, is very low for productivity. So can we have a solution which is both high performance and high productivity, where the user can just do an MPI send and an MPI receive by passing the device buffer, and inside the communication runtime, we are able to stage the transfer in a high performance way. So this core idea is what evolved to be the MVAPICH2 GDR MPI library, which is aimed to provide high performance and high productivity to users. Okay. Now, inside the library, there are a bunch of things that we do to improve the performance. And we've been doing this for the last several, like 5+ years. So this initially started off as a collaboration between NVIDIA and us. We have a lot of different support over the last, like, I don't know, 10, 15+ releases of the MVAPICH2 GDR stack. Okay. And these are some of the prerequisites. At this point in time, we do have support for the AMD GPUs as well as the NVIDIA GPUs. And this is how you download and use it. And this is the latest set of features that we added for the MVAPICH2 GDR 236 release. Okay. So two of the biggest changes that we made was adding support for on-the-fly compression of messages and adding support for an integrated MPI plus nickel hybrid solution for collective operations. So using this, we were able to add full support for the NVIDIA DGX, DGX2V100 and DGX2A100 systems with enhanced support for architecture detection, process placement, intranode, internode, point-to-point tuning, as well as collective tuning. So all of this was made possible because we got access to the Theta GPU system. So you may believe it or not, even though the DGX systems have been available for the last, I don't know, 3 years or so, we only got access to them about 3 months ago. So till then, we never had access to a DGX system. So that is one of the primary reasons why we were not able to optimize the MVAPICH2 GDR software stack on that platform. So recently, we were able to get access, and with that, we were able to do a lot of changes in just a matter of 3 months. And we were able to make this release. The latest MVAPICH2 GDR release also has support for CUDA 11.3 because it has some changes in the way you can intercept the communication libraries. And we also have support for ROCm 4.3, not 4.1. We have support for ROCm 4.3 for the AMD GPUs. And as you will see in the upcoming talk by Amir, Arpan, and others, MVAPICH2 GDR also has support for a lot of the newer deep learning and task and QML kind of frameworks, and more details about this will be covered in the next tutorial. So GDR has a lot of interesting features based on some capabilities that vendors like NVIDIA and Mellanox came up with. So we have support for features like GDR copy, GPU direct RDMA, and a lot of environment variables to turn this on and off. So all of this is turned on by default, But if any of your systems does not have any of these libraries, then the MVAPICH2 GDR software package will print out an error message based on which you can enable or disable appropriate features so that the overall code still works fine. Okay, so more details about this is available on the GDR user guide. Similarly, we have designs for tuning loopback. So there are different ways in which we can transfer data from a GPU to like a remote GPU. So either using GDR copy or GPU direct RDMA, or using a loopback based network, loopback based transfer, or using CUDA memcopy or CUDA memcopy async. So there are like a bunch of different ways, and we have explored all of these in a systematic fashion, published papers on these, and then made them available as robust code for end users. And there are different environment variables like GPU direct limit on the sender side and on the receiver side that you can tune to get the best performance. Now, why are we providing all of these environment variables to you? So we have tuned all of these variables on a bunch of different systems, but there could be a new system that you have where these are probably not the best. So that's why we are trying to expose these environment variables to you, so that in case the default tuning is not good enough, you can try to play around with some of these things to see if it helps you improve the performance any better. Through all of these efforts, we were able to improve the performance of applications like HPC, which is a molecular dynamics application out of the University of Michigan, by a significant margin for a different number of processes. Okay. We also have support for advanced data type processing inside MVAPICH2 GDR. So we support a lot of different vector types. We use separate non-blocking streams so that there is no serialization happening. We have different parameters to tune kernels for vectors. We have these parameters to tune them. We have some other parameters to tune for the subarray data type, and some other parameters to tune for the indexed block data type. So using all of these things, we are able to give overall good application performance for data type based communication. So this is an example of a 3D stencil, like a 9-point stencil here. I'm trying to see the performance of the advanced data type based solutions that we have inside MVAPICH2 GDR compared to the default versions. Okay. So we also worked with organizations like the Swiss National Supercomputing Center to see if we can accelerate some issues that they had in data type processing for some of their applications. So there, what we ended up doing was, previously your data types would get serialized. Okay, so if you have one ISEND, you would initiate the kernel, wait for the kernel to complete, and then perform the send. So what would happen is that there is a huge wait time here, which is more or less being wasted. So what we tried to do was to see if we can use non-blocking kernels and multiple of them, so that we can initiate multiple ISENDs at the same time, thereby overlapping these kernel processing time on with the launch time of the other kernels. So broadly, what we were able to do was we were able to significantly reduce the overall launch and execution time of the data type processing on the sender side and on the receiver side, thereby leading to significant benefits in overall application execution time. Okay, so this waste of computing resources is what we were able to avoid. Now, the upshot of all of this was that we were able to significantly accelerate the weather forecasting for Switzerland. So the Swiss National Supercomputing Center uses what is called as the COSMO model. And through our proposed solutions, we were able to improve the overall performance of the COSMO model by a significant factor of 30% on 96 GPUs on 8 nodes. So this was something that we are very proud of. So through our work, we were able to actually improve the performance of weather forecasting in Switzerland. So this was a work done between us, the Swiss National Supercomputing Center, and Meteor Swiss, which is the weather forecasting agency in Switzerland. So we didn't stop there exactly. We continued with our data type work, and we were trying to see if we could use other kernel-based and GDR copy-based mechanisms to perform optimized data type packing and unpacking methods for other applications like the comb application from Lawrence Livermore, as well as some micro benchmarks which mimic application behavior like MILK. So as you can see in these slides, through our optimized schemes, we were able to get significant speed up. So this is execution time and this is speed up. So here higher is better and here lower is better. So what we are able to see is that through our zero copy pack-free designs, we are able to significantly improve the speed up and reduce the overall execution time of applications that use dense data types. Okay. So far we've been trying to see and show how you are able to get improved performance for like a lot of applications without actually messing around with the buffer that the application gave. Okay. So now, recently we have begun to explore the capability for on-the-fly compression for GPUs. So why on-the-fly compression? What is the architectural trend that is making this more useful? So mostly if you look at modern applications, they are trying to run with larger problem sizes because there is a lot more compute that is available, which means that the applications are exchanging orders of magnitude more data in the network. This leads to a significant increase in overall execution time, especially in the terms of communication for applications like AWP ODC and P3D FFT, which does dense communication across the network. If you look at most modern HPC systems, there is a significant disparity between intranode and internode communication. Now, DGX2 is an exception where you have an abundance of DGX2 or DGX2-like architectures, like of those you have on the Microsoft Azure platform, are exceptions where you have 8 HDR network adapters. But that is not the case for most systems, where your internode bandwidth is significantly limited compared to your intranode performance. Okay. So on these kind of systems, without your high performance mechanisms, your internode communication can become the bottleneck. So can we alleviate this architectural issue? So that is the basic trend that we were trying to address as part of this work. So what we did was we tried to use existing available compression, GPU-based compression libraries like MPC and ZFP, and attempted to see if we can integrate that into a communication runtime like MVAPICH2 GDR and provide seamless compression, on-the-fly compression capabilities to end applications so that we are able to shrink or compress the data that is being transmitted on the fly without sacrificing on correctness. This is the most important part. Just because you're compressing the data doesn't mean that your data validation is going wrong. Okay. So we are trying to compress the data while ensuring that the validity is there. Okay. So we explored 2 different compression algorithms. So our compression libraries, one is MPC, which is a lossless compression library, and the other is ZFP, which is a lossy compression library. So this is all you have to do. So with MVAPICH2 GDR236, if you enable these parameters, then you will be able to achieve compression. Okay. So if you are interested in using this, please send us an email. We will provide you with the right set of RPMs with the features enabled, so that by just setting these 3 environment variables, you are able to test out the performance of GDR with and without compression at the application level. Okay. So these are the list of environment variables, additional tuning environment variables that you have here. So by default, these are the only variables that you need. So you need to enable CUDA support. you need to enable compression, and you need to choose the compression algorithm. For MPC, it is 1, and for ZFP, it is 2. Okay. Now, if you want to do any additional tuning, these are some of the variables for you to do that tuning. So these are, this is to choose the messages after which you want to use compression for internode communication and intra-node communication. This is the dimensionality, and this is the compression rate that you want to provide ZFP. Okay. Now, what is the upshot of all of this, and what is the big deal? So the big deal here is that by doing all of this, we are able to significantly improve the performance of real scientific applications like AWP ODC. Now, AWP ODC won the NVIDIA Innovation Award several years ago for their innovative work on the NVIDIA GPUs. Okay, it is an earthquake simulation application. So for that application, for their production runs, we were able to significantly improve the overall execution time of the application on very large, up to 512 GPUs. We were able to show 18% improvement in overall application execution time. I'm not just talking about your communication time. This is about overall application execution time. So that is a fairly large deal, especially when you are looking at large-scale applications, including deep learning applications, which transfer vast amounts of data. Okay. So, any questions on the on-the-fly compression support before I proceed further? Okay. If not, let me proceed. So, as I mentioned, we only recently got access to the DGX2 system, and we were able to do a lot of work there and significantly improve the performance of our collective solutions compared to Nickel on those platforms. So here I'm showing some sample performance numbers for collective operations on the DGX2 800 system. So here we are looking at the small message performance for all gather, broadcast, reduce, and all reduce. So as you can see, in the small message range, we are able to significantly outperform the Nickel-based collective communication, or the Nickel collective communication library from NVIDIA for all these different collective operations. While on the large messages, we are able to match Nickel's performance for all the different collectives. So this is on 4 nodes with 8 processes per node. For a total of 32 GPUs on the DGX2 A100 systems. So this is for a small number. So how does the performance look when we go to much larger scale? So that is what we are trying to look here. So this is the performance of MVAPICH2 GDR for MPI all reduced at scale on the Oak Ridge Summit supercomputing system. So here we are looking at like 2 different things. So we are looking at the performance of all reduce for latency as well as bandwidth at 1536 GPUs. So we can see that compared to like Nickel version 2.6, we are able to significantly better at such large scales. Okay, and this directly gets translated to the performance of TensorFlow training. So here we are looking at the overall bandwidth we get comparing different MPI libraries like Spectrum MPI, Open MPI, Nickel, and MVAPICH2 GDR. So this also leads to significant benefits. For more details, please look at this paper. So we also have advanced support for the AMD GPUs here, not just the NVIDIA GPUs. So if you, these are some sample performance numbers taken on the Lawrence Livermore Corona cluster with MI50 AMD GPUs. So compared to OpenMPI, we are able to get very good internode and intranode point-to-point communication, as well as like very good performance for reduction collectives like all reduce at 8 nodes with 8 GPUs per node for a total of 28 GPUs. And for, like this is 64 GPUs, and broadcast as well with 8 nodes and 8 GPUs per node. So we get significant benefits compared to other MPI libraries like OpenMPI here. So with that, we kind of come to the end of the GDR section, and we'll go into some application-based tuning. So we typically, what we do is we work with a lot of our collaborators, and we try to see what we can do to improve our performance further for applications directly. So we took a bunch of different applications and tried to see what we can do to make the performance better. So one thing that we have consistently found is that by increasing the eager threshold, we are able to get better overlap of computation and communication, better asynchronous progress capabilities. So even though the raw performance may not be as good, because of the ability to progress communication asynchronously, we are able to get benefits at the application level. So we have seen this for a lot of different applications. So in this instance, we are looking at the Amber application. So we see that by tuning the eager threshold to a larger value, as is described here, we are able to get 20% benefits in the application execution time. And same for the mini AMR application. By pushing the eager threshold beyond, let's say, 32K for this particular problem size, we are able to reduce the overall communication time by 8%. Okay. So if you guys are using any applications which use a lot of non-blocking point-to-point operations, then this is something that I would definitely suggest trying to tune to see if it leads to improved communication performance. Okay. So similarly, what is the impact of transport protocol at the application level? So here we look at the performance benefits of using the UD transport protocol versus the RC transport protocol for the SMG 2000 application. So this uses a lot of dense communication operations. Okay. So we see that we are able to improve the performance by up to like 20% for like very large number of processes. So by forcing the UD protocol, we are getting much better scalability at larger scales for applications. So this is also seen not just for the SMG 2000, but this is also seen for the Neuron application. If you recall, on the MVAPICH2 side, we used the DC transport protocol to get better performance. So here we were using the open source MVAPICH2 library. So we are just using the UD protocol here. And these are the details of how we ran it and what sort of benefits it provided. Okay. So going forward, MVAPICH2 has support for system-specific collective tuning. Now, why do you need this? If you look at different kind of HPC systems, they have different communication characteristics, different architectural characteristics, which leads to a lot of choices to how you orchestrate the communication. So, for instance, if you have like a 128 core system versus maybe like a 16 core system versus a 64 core system, the kind of intranode communication primitives you use and the kind of algorithms that you select may be different. So unless you select the right algorithm for the right system size and the right message size and the right number of processes, you will not get the best possible performance for your collectives. So this process is called collective tuning, and we have done extensive collective tuning for different HPC systems to make sure that we get the best possible performance. Okay. So the upshot of all of this collective tuning is that we are able to select the right algorithm at the right system size, at the right message size for the right application. And that leads to significant benefits in execution time for different kind of HPC applications. Like here, we look at the HPCG application, where the tuned version performs up to 24% better than the version without collective tuning. Okay. So all of this is available by default. You don't have to do any changes to your library to achieve this. So we also look at the GDR side of things. And as we mentioned earlier, these are the environment variables that we have used. So if you want to try the Blue application, please download it from the University of Michigan website. get the GDR package you want from the MVAPICH2 download page, set these environment variables, and you should be able to reproduce this performance numbers. Okay. So we also evaluated the performance and application scalability on Skylake with KNL and OmniPath. So as you can see, with a lot of applications like MiniFE, Neuron, and Cloverleaf, we are able to get very good scalability trends for like all the different applications that we see here. So the first set of graphs on the first line were taken using the Skylake architecture. The second set was taken using the KNL or Knight's Landing architecture on the Stampede 2 supercomputing system. So here we look at the performance of MVAPICH2 versus Intel MPI on a range of different spec benchmarks on Broadwell plus InfiniBand. So as you can see, MVAPICH2 is able to outperform Intel MPI on almost all of these benchmarks by a fair margin. Okay. So with this, we kind of come to the end of our tutorial, and let me try to conclude with a brief discussion about the future plans for MVAPICH2 for exascale. So far we discussed a lot of things that we had introduced as part of our current work. So I want to give a brief, let's say, glimpse about what is coming in the future. So we want to add support for the MPI plus task model. So we are also working on using some of the advanced features from Mellanox, like hardware tag matching, using adapter memory, blue field based offload. So the Xscale Solutions folks will be talking about the benefits of blue field based offload and talking about some of the products that we had made based on the research done at research work that we had done. And we are also trying to see how we can use the upcoming compute and communication architectures like ROCm, Intel Optane, Bluefield, and CAPI to give overall better communication performance. And some of these will be available, are already available, while some of them will be available in the future releases. Now, before I conclude, let me give some pointers to some of the other interesting talks which we'll be discussing about MVAPICH2 and related features. So Dr. Samir Shende will be talking about the tools support in MVAPICH2 and how you can performance engineer your application with MVAPICH2 and Tau. Jitin will be talking about MVAPICH2 on Microsoft Azure. Matt Cope will be talking about how some of the service options and hardware choices for HPC on AWS. Todd Gamblin from Lawrence Livermore National Labs will be talking about some updates on binary cache handling. So this is something that is very essential for us to deploy MVAPICH2X and MVAPICH2 GDR binary packages using SPAC. Honggang Lee from Red Hat will be talking about how we work with Red Hat Enterprise Linux to integrate MVAPICH2 into RHEL. And our students, who are the real heroes here, will be talking about what they are doing in a series of short presentations Tuesday and Wednesday in the evening. So please do attend that. Okay, that is a sneak preview into some of our newer features that you'll be seeing in the next few releases. Let me conclude with funding acknowledgement to all of the organizations who are and who have funded us who are funding and who have funded us in the past. But most importantly, our staffs and our students, these are the real heroes. So we go to a lot of places and present talks and give tutorials. But these are the guys, the students, the staff members, these are the guys who do the actual work, make sure that the project and the product is in a stable fashion and is available for everybody and the community to use. So with that, I'd like to wind up. If you guys have any questions, I'll be more than happy to take it. If not, Amir, Quentin, Arpan, and others will be talking about how deep learning applications and machine learning applications can utilize MVAPICH2 GDR. Thank you.
Thank you, Hari. I don't see any questions on Slack, but I can ask a few questions if you're okay with that.
Sure.
Sure. So for the compression, is compression limited to any particular data types?
So at this point, the compression happens inside the MPI library, and it happens after all the data type processing has taken place. So it is applicable potentially to any data type. So the compression happens after the packing is done and just before the send happens. So it is applicable to any data type. So not just your regular ones, but it is applicable to anything.
All right. Okay. And this includes derived data types too, right?
Yes. Yes. This includes derived data types as well. That is correct.
And does the current release support compression support for collectives?
Yes, in a naive way, it does. So so if you look at the MPI stack, the collectives are a layer on top of the point-to-point support. So they are layered. It's a layered architecture. The current compression support that we have is at the point-to-point level. So the collectives code can automatically take advantage of them. However, it may not be fully optimized. So we are exploring specific solutions for using compression at the collective level. So yes, they are applicable for collectives, but it may not be the best possible yet.
Okay. Okay. Sounds good. Sounds good. So what were the most technical things that MVAPICH2 team tackled, while supporting GDR on DGX systems?
So a few things, a few interesting things were topology mapping. So figuring out the network topology, using the right GPU for the right network adapter, supporting more network adapters, figuring out how to get the best performance for HDR adapters, which included using multiple endpoints, and trying to make the best utilization of the rich intranode network topology. So MVAPICH2 GDR historically was made to work around all the different hardware limitations which initial GPU-based systems had. The DGX system happily has very few such hardware limitations. So we basically had to like rip out a lot of the older code, which were meant for, let's say, not so good systems, like in a hardware or in an architectural perspective. So these were some of the more interesting things that we had to do. That's a very nice question. Thanks.
Okay, sounds good. Sounds good. So with that, I would like to thank you, Hari, once again for all the effort that you and the team is putting into the MVAPICH2 software. So for all the attendees, if you have any other questions for Hari, please post them on the Slack channel.
Sure. Thanks, Amir.
Thanks. Right. So